Welcome to Advanced Data Analysis 2 with me, Erik Erhardt, Professor of Statistics at the University of New Mexico. In this video, we'll continue Chapter 5, finishing the Beetle example, and address issues of non-constant variance in the two-way with interaction model. So we'll jump over to the notes. So we're going to start here with checking model assumptions, but I want to remind us back on page 125 what the data look like. So here are the Beetle data, and the plot on the left is the one I prefer. We've got insecticides as different colors. We have dosages low, medium, and high going horizontally, and then we have the hours in units of 10-hour blocks for that the beetles survive. And we basically see that beetles survive a long time for low dosages, and as you increase the dosages, they survive much shorter, and that the insecticides seem to make a difference too. For example, insecticide B, if you're a beetle, you'll survive twice as long than if you're on insecticide A. All right, so let's jump back to page 138 for checking the model assumptions. So we care about the residuals. All of the model assumptions are always on the residuals of the model. We care that the residuals are normally distributed and they have constant variance. So let's take a look at these plots. So in particular, we're looking at the constant variance assumption. So here we've got insecticides are different colors, dosages low, medium, and high, but on the vertical axis, yep, it is the same as before. Okay, this is the same plot as that we just looked at on page 125, except there aren't the lines connecting the means. But what do we see here? We see, in particular for the high dosages, we see very little spread, whereas for medium and low dosages we see high spread. So is there a relationship here that we should be worried about? So one way to address this is by plotting the mean versus the standard deviation. So we have colors, which are insecticides. We have the shapes being the different dosage types. And so all the squares, which are the high dosages, have low means and low standard deviations. And the others are basically all spread out. Okay, the low and the mediums, the circles and the triangles. But there definitely seems to be some dependence here between mean and standard deviation. It's hard to know exactly what that relationship is, whether it's linear, whether it's sort of curved upwards, as these 2 points suggest, or whether it's sort of curved downwards, which this 1 point suggests. The point is that there is some sort of relationship here, and we want to address that. So before I continue on, I want to scroll up and show you how I created those plots. In particular, we used, so these 3 lines of code here are just the left-hand plot. It's sort of remarkable how powerful ggplot is. Horizontal axis dosed, hours 10 is the vertical axis, colors are insecticides, give me box plots. That's all it is. All right, for the plot on the right, I used plier to separate, or that is split, the long data frame by dose and insecticide, and I summarized each four observations in every combination of dose and insecticide. I calculated the mean and the standard deviation, and then I returned that into this object, and I got this little table. Oh, should not scroll down like that. All right, so I get this table with means, right there's the M, and then standard deviations. And all I'm going to do is plot these pairs of numbers with dosages were shapes and insecticides were colors. So that's all that's being done here. Shape is dose, color is insecticide, give me some points. Size equals 4 just makes the points a little bit bigger so they're easier to see. Done. All right, so how are we going to address this non-constant variance? So let's look at the rest of the diagnostics here. That non-constant variance we're seeing in this top left plot, we've got the fitted values. Okay, so lower values indicate that we're predicting shorter survival times, and the higher fitted values are predictions of higher or longer survival times. And we definitely see this very tight cluster for low survival times. That's for those high doses. And then when we've got long survival times, lots of variance here. I'm not actually too worried about these three influential observations because we have non-constant variance, and look at this normality plot. So this S shape, I recognize that's not how you draw an S, but if you flip the S around, that would be a bad looking S. That's because of this non-constant variance. Basically, this has high kurtosis. It's very peaky in the middle, and then there's lots of spread also. It's called leptokurtotic. All right, that's all what that paragraph says. All right, so I've discussed all that. Let's think about ways to fix this non-constant variance issue. And a transformation here is typically the strategy because if you want to use a standard regression model. Alternatively, you could use a non-parametric strategy, in which case a transformation may not be necessary. But if we want to do standard analysis and meet the normality assumption and so on, and equal variance, we can do a transformation. So there's 4 situations that I'm give suggestions for, depending on the relationship between the standard deviation and the sample mean. Basically, that plot we created on the right above. So if S is basically independent of Y, then there isn't a dependency, and so don't transform it. We hope that all the standard deviations are basically equal, but if they're not, but they're independent, then there isn't a straightforward transformation to think about here. The other 3 gives us different transformations for different relationships. So this first one is if they're basically linearly related, we can try a log transformation. If they're quadratically related, we can try a reciprocal, or the inverse. That is, if we had the number 5 hours, 1 over 5 would be 0.2. So we'd take the reciprocal of each number. If there's basically a square root relationship, I'm motioning it with my hand. Can't you see that? Sort of, it starts steep and then it becomes shallow as it heads off to the right. That we might consider taking a square root transformation of the response variable. In our case, there isn't a clear suggestion of one of these, and so we might select the one that makes the most sense or is easiest to interpret, and then check the model assumptions to see if we still have an issue. And that's what this paragraph basically says. We can try a logarithmic transformation, but I'm going to try the reciprocal because it has the interpretation that this is the dying rate. Okay, so 1 over time is a rate. It's so that higher rates indicate that you live shorter because events happen more quickly. That's what the rate indicates. All right. So let's create a rate variable, which is just going to be 1 divided by the hours. And we'll just redo all the analysis, replacing the response variable as rate. All right, so I'm recalculating means and standard deviations in terms of rates, and I'm going to also look at that box plot using y equals rate. I'll scroll down and take a look at this plot. So same plot as before, but now the response variable rate is on the y-axis. And boy, when we look across these box plots, they're not that different, not like before. When we compare the mean versus the standard deviation, there isn't really a clear pattern here. There's definitely some variability in standard deviation, right? There's a 0.2 down here, and there's a 0.8 up here, but it's not related to mean. Furthermore, we have to always keep in mind the sample size here. 4 observations doesn't give us a good estimate of the standard deviation. It doesn't even give us a very good estimate of the mean. Something I've never mentioned, I don't think, in this class is that Tukey gave sort of a rule of thumb for how many observations you need to estimate moments of a distribution. A moment of a distribution is powers of the expected values. So the mean is the first moment, the variance is the second moment, skewness is the third moment, kurtosis is the fourth moment. And the number of observations he suggests you have is at least 5 to the power of the moment. So 5 to the first power would be, you should at least have 5 observations to estimate the mean. 5 to the second power is how many you should have to estimate the variance, of which the standard deviation is the square root. So we should at least have 25, and so on. It sets a high bar for skewness and kurtosis at 125 and 625 observations at least. But the point is to give some perspective that these variances are not well estimated. So let's not worry too much. All right, let's go ahead and calculate all those means and so on, create some plots like we had before, and here we go. Now we've got rate on the vertical axis, and the plot I prefer here is the one on the left. We've got insecticides are different colors, and dosages are on the horizontal axis. We see, insecticides A and B are higher than insecticides D and B, and we see this pattern of basically it starts low, heads up a little bit to get to medium, and then heads up a lot to get to high. There's that sort of pattern. And, there's some non-parallelism here, but these are not too bad. If we look at this plot too, we see, it's almost looks like parallel lines to, accounting for variability, right? So let's fit our regression model. So here's our linear model. We've got rate as the response variable, and dose times insecticides gives us the 2 main effects as well as the interaction. And when we test the interaction, it is not significant. Variable. We no longer have the interaction, which is what we had previously when we used hours as the response variable. So there's 2 great things that just happened. The first thing that, okay, maybe I haven't convinced myself yet. Well, I guess I have. Okay. I want to look at the residual plots. Okay, let me come back for a second. So we're going to update the model and drop the interaction term, and both the main effects are significant. Okay, let's take a look at here's the big news. Take a look at the residual plots. So, these residual plots look beautiful in terms of the fitted values. It looks like we have maybe one influential observation. It's sort of twice as influential as the next 5 or so values. It's maybe worth looking at. It's one that's sort of in the middle in terms of the fitted values. I don't know. So we could remove it and see if our inference changes. Constant variance looks pretty pretty good here, and normality looks really good. And the second great thing that happened, okay, so the first great thing, residual plots look great. Second great thing is that we no longer have an interaction. We only have these two main effects. So the explanation of the data has become simpler. So we can describe the relationships between insecticide and dosage just by interpreting main effects and not worrying that everything depends on everything else, that the effective dose depends on which insecticide you're using. That's no longer an issue for the interpretation. So it's really great. So we can wrap up by comparing levels of each of our main effects. We'll compare doses and insecticides using the general linear hypothesis test. We can also use the LS means function if we wanted here. We're going to use Bonferroni adjustments. What we find here is for doses, medium and low are not different enough to be considered different from using the Bonferroni correction. So medium and low are, we can think of as being the same, but high is, high is different from both low and medium. Okay, we have significance there. So that would suggest, based on these numbers, that medium and low basically the same, and then there's a jump, there's this increase when we get to high. Okay, so we'll keep that in mind when we're about to go back and look at the plots. And then for insecticides, we've got 4 insecticides, so there's 6 comparisons here. Let's just look at the ones that are not significant. So here we've got C and A, not statistically different, at least at a 0.05 level, and C and D, oh no, that's not it, D and B, excuse me, are not different. Okay, so B and D are not different, A and C are not different. Okay, let me page up to the plot and see if this makes sense. So what we found was that low and medium doses were not statistically different. Okay, so it's sort of roughly horizontal, and right, you're looking at the red and blue and you're saying, Eric, that's not horizontal. I get it. But relative to the variability, we don't have enough evidence to say that these two are different. But then there's a jump when we get from medium to high, and also, of course, low and high are statistically different. So that's the main pattern for doses. When we looked at insecticides, we saw that A and C are not different. That's the red and the blue. That's these two top ones. Those are not statistically different. You might believe that just by looking at the plot and how much variability there is here, as well as B and D, the green and purple below. Those are not statistically different. So all the hypothesis tests are supporting features that we can see right here in the plot. All right, let me page back down. All right, and the last thing we have here is a plot of those pairwise comparisons. You can see here that C and A are right teetering on the edge, right? Well, so that's what you get for, you got to make good choices about the ways you're going to do hypothesis testing, how you're going to do corrections for multiple comparisons, all those things beforehand. Because once you actually perform the test and see the results, you don't get to change how you do things. That's called cheating. All right. So the comments on the 2 analyses, I believe I've pretty much covered all these things. Maybe I'll just say that we used that inverse transformation for the rate, and all the assumptions seemed to be met. We had nice interpretation that a rate has, that the number of events per unit time, and so so I think we'll just stick with that. We could also look at the logarithmic transformation, and if you'd like to pull the code out and do that, you can tell me what the result is. I would predict that we're going to get pretty much similar things as with the inverse transformation in terms of the assumptions being met, and maybe we only have a main effects model there as well. So, great. So in the previous video, we looked at the means and LS means, and so we'll come back in the next video to talk about unbalanced designs, where we have a rat insulin example.